Hello, everyone. Come on in. Feel free to ask questions while we're waiting for everybody else to come in.
Hey,
What's up, Andrew?
did you have a lecture on Monday? Or
Yeah, the school was closed, so we had no lectures.
okay, because you had a link for one on September 2nd, and I didn't realize it, so I thought maybe you had a lecture or something.
Yeah, it just there's a way I could possibly do that, but basically when I set up the Zoom links, I set it every Monday and Wednesday, and I could go back and cut out the days that we have off, but I just never do that. So sorry about that. Yeah, feel free. It looks like some of you are already doing it. You're
No problem.
adding your first and last names. Please do that for roll. You can do it now or you can do it later, but just make sure you don't forget.
Yeah, I noticed that too with the Zoom for Monday, but I checked the syllabus and noticed that all the dates I think are like a day off.
Oh, now
Because I
that's
was seeing if it listed that day off and it showed September 3rd was class, not September 2nd. So I think they're like
gotcha.
it's a
Yeah,
day
that
off.
could have been the problem too. That doesn't help, but hopefully I got all the Mondays and Wednesdays right within the Zoom uh reservations basically. So at least that part works. Anybody have any other questions? Any problems you had with the homework, for instance, doing estimating problems and that sort of stuff? I told everybody before, let me go ahead and make that announcement again in case somebody didn't hear me. When you're doing your Pearson homework, uh, you can try to get as good a grade as you want if you really want to, but there are instances where Pearson has problems that actually have mistakes built into them, and not on purpose. It's just ones they've missed over the years. So occasionally, if you're trying to actually get that perfect 100 score on your homework, there's going to be an instant where you might actually be forcing yourself to learn how to solve a problem incorrectly to get the right answer, and that's never a good thing for people. So uh, do what you want in terms of if you want to keep your grade up. But what I'm going to tell you is all you should really care about is making sure you get like a 75 or better, and then learning what you did wrong on the problems you got wrong, and questioning whether or not, of course, whether you really did get them wrong, because again, there are potentially some wrong problems in there. But once you've gotten, like I said, a 75 or better, and you figured out what you did wrong on the ones you got wrong, I think the time that you spent on your homework is enough at that point. If you want to go ahead and continue to get your grades higher, that's great. But what I'm going to do is about 2, 3 weeks before our final exam, you're going to have the option to tell me, hey, I'm really worried. My homework grades are jacking up my class score. And I'm going to offer you a way of addressing that. And I'm confident you'll be happy with that way of addressing it. But, just in case, like I said, if you want to continue fighting for a perfect score on your homeworks, just to make sure your grade comes out of it being A, that's fine. You can do it. But I would really advise that that's probably a little bit wasted time. So just keep that in mind, that the 75 and understanding what you missed and how not to miss it in the future is a plenty good score. And from there on out, you want to probably focus on just taking the practice tests. Additionally, if you're looking at problems of what I call the Fermi calculations or the estimates or order of magnitude estimates that we covered in chapter one, if you're doing those on the homework, it can be very hard and confusing. Whereas if you start taking chapter one practice or chapter one and two practice tests, you'll start to see what kind of estimate problems we have on the test. And I think you'll find those are a little easier to understand and a little easier to do. They're questions like, on average, how many times does a human's heart beat during their whole life? So that requires you to estimate roughly how many beats you get per minute and roughly how long a human lives, right? And then just doing the math. that's a lot more reasonable and a lot easier than trying to guess, for instance, roughly how many fruit flies fit in a 9 by 9 by 3 meter room. So just keep that in mind. There's other ones like how many pennies can you fit in a box, and they'll give you the dimensions of a box and stuff like that. Those are a little bit more straightforward. So just keep that in mind. Anybody have any other questions? I felt like I might have interrupted someone when I started reminding myself about the story about the grades on your homework. Anyone?
I've been having issues with Pearson's, so I can log into the classroom, but none of the assignments are popping up. And it's just for my physics one, like my math one, I've had no problems, but I can't physically see anything. And I've tried logging on in like different ways with different computers, but I still have no luck.
So I'm checking your. I just paused the recording for some stupid reason. I'm gonna look. I actually have my Pearson open right now. I'm gonna look and just make sure your name is actually listed in the course, because if it's not, that's obviously a problem. So let me look at that. Gotcha. I was just double checking what your name was to make sure I knew. So your name is definitely in the grade book. And I see all the assignments listed under your name. So I'm not sure what's going on. You might need to empty your cache in your browser and then open it back up. That's always the first thing you want to try when you're working with an online homework system, is just empty your cache and then reload the page. I don't see any reason, and I can't understand any reason why Pearson would put you in the course without you seeing the assignments. Now, when you do go to the course, are you going through Canvas to get there?
Yeah.
And what's the first screen you see when you get there?
I can, when I log in, I see my classes, my math class and my physics. And when I click on the physics, I can't see any assignments. All of the tabs are blank.
Okay, are you using an Apple product?
I am, but I've tried it on different computers as well.
Okay. One thing I would say, don't use Safari. Safari does better than, for instance, Microsoft Edge, but it's still not that great. So I would definitely recommend you use Google Chrome or Firefox for your browser, and
Yeah.
everything should work at that point. I'm wondering if your pop-up blockers are up, so you want to make sure they're turned off. But when you get to your course and you click in it, there should be an option for you to click on something that says all assignments or something like that. Or
Yeah, I don't have that option. Like when I go into the class, it just reads scores, like the study area, the document sharing, but there's no assignments.
it's so weird. Yeah, you're definitely going to need to contact Pearson on that one. And
Okay,
do it soon. But keep me in the loop, because I can push your homeworks back, which, by the way, I went ahead and pushed everybody's chapter 1 homework back to be due on this coming Sunday. And that puts
okay.
chapter 2 not due until like the 13th or 14th or something. And that might actually work out pretty well given the way we're doing class. But yeah, definitely call Pearson and find out, because that's something going on with yours. But I definitely empty the cache, because it could be something as little as it just can't load that particular screen. Make sure you've got
Yeah.
your pop-up blockers turned on, because it could be something as minor as it's not opening that. But yeah, that's weird. I've never had that happen.
Yeah. The only thing I could possibly think of is I'm a high school dual enrollment student, so I don't know if that affects how some of my stuff comes up, but that's the
I,
only other thing I could think of.
Yeah,
I'm also
it
doing that, so
shouldn't
it's
be
fine
that,
too.
because even, I mean, if your school, if your public school was actually in the loop, meaning that you had to go to some website on their uh, server, that could be a problem. But I don't think any of that's going on, so it shouldn't be that. But yeah, definitely call Pearson. And being 2, 3 weeks in, this is probably a good time. You won't have too terribly much of a wait to get there.
Okay, thank you.
Okay, so let me know what happens. Feel free to text me with this. That way you can get it to me in a quicker time
Sure
period
thing.
as opposed to emailing me. Okay?
Awesome. Thank you.
No problem. Remember my phone number's on my syllabus if anybody needs. I do have syllabuses for the labs too. But I discovered that I really wrote the calendar backwards. Like my class that have Monday labs, I put on Wednesday, and the class that I have Wednesday labs, I put on Monday. So I got to fix that, but it doesn't matter for you guys because someone else did your lab course. Any other questions before we move on? Okay, well, we're gonna,
Professor,
yeah, go ahead,
sorry,
Alex.
just one thing to add. I mean, maybe Lillian, you already tried this as well, but I had a similar issue, and for me, it was the pop-up blocker. I don't know why, but like I had the same thing. Like I'd open up Pearson and it would say course home, everything would be blank, and I would just have scores, purchase options, the study area, and that stuff. And for whatever reason, it was opening a separate pop-up with
Gotcha.
literally the same page, but it just had the assignments on it. So I like it's kind of annoying to work through that pop-up, but at least like the assignments were there. But it took me like 3 or 4 tries because you see course home and you think you're in the right spot. But if you, I mean, obviously you've already done that, then Pearson's probably the best way. But it
Yeah.
took me a
Oh,
couple
yeah, I'll
times.
definitely try it again.
Yeah, the pop-up blockers, they can be a problem, and it's weird because not every browser pops up at the same time as every other browser. So it could
Yeah,
be something as minor as that. So yeah, definitely make sure you check that out. Thanks for that. That was Alec, right? Yeah, thanks, Alec.
yeah, no problem.
All right, so we have essentially finished chapter 1, and that was mostly about some things that I didn't even get a chance to talk about that much because I have videos on my YouTube channel for that, and some of it's really straightforward. But you need to understand the SI system of units, those prefixes, and then of course what the base units are. You do need to be able to do what we call unit or dimensional analysis. I like to work with dimensional analysis, and the difference being like if I said the unit of force would be kilograms meters per second squared, which is actually what we call a Newton. If I tried to do that in dimensional analysis instead of kilograms meters per second squared, I'd call the dimension to be m times L over T squared, where the M and the L and the T are all capitals. That's really the only difference between unit analysis and dimension analysis. But you should be able to have me tell you, hey, this quantity, energy or power or force or whatever has these specific units or these specific dimensions. And we assume it depends on mass, length, and time. Can you write out a dimensionally correct equation with that in mind? And then you'd say mass raised to the p power, length raised to the q power, and time raised to the s power. And then you proceed to solve for p, q, and s. That's dimensional analysis, and you need to be able to do that. So make sure you can do that. Make sure you understand about basically what the fundamental unit is. Like, for instance, we now have a unit of 1 second defined in terms of a certain atomic clock and what it does. And then we have the unit of distance defined in terms of the speed of light, stuff like that. But like our unit of mass, I think is still a specific cylindrical shape of platinum and iridium that's kept in a room where all the temperature, sunlight, I was looking for vapor pressure and all that good stuff are all exactly the same. So those things are important. Know how to convert units. That's probably the most important thing that came out of chapter 1, and then understanding the scientific process and that sort of stuff. So that was just a little quick recap of chapter 1. In chapter 2, we're learning about kinematics, specifically in one dimension. So we're imagining one-dimensional motion, and we're going to lead into a discussion of vectors versus scalars. And they're doing the introduction to one-dimensional motion with that in mind. So they're imagining that all the motions happening in chapter 2 are happening along like the x-axis. The reason why is because we can actually then define something that's very much like a vector And then we can define something called speed and something called velocity. And the two of them differ by a very specific thing. So all of that is what we're doing in this particular chapter. So just be aware of that. What I want you to do always in your physics is try to think what about physics is like stuff you already know. In other words, I don't want you fixating on, wow, how weird that is. Or, I mean, even though I find, the weird facts of physics, like, time slowing down when you speed up, or uh, quantum mechanics suggesting that a particle has no particular location in space until you measure it. Those things are really super fun to get you excited about physics. But in learning physics, the coolest thing about it is when I took chemistry and physics my first semester in college, I thought physics was a lot easier than chemistry, specifically because physics was more related to things I'd already done and experiences I already had. And therefore, I was constantly using what I'm used to dealing with to make sense of what I'm learning in a physics class, where it was a little harder for me to do that in chemistry. Maybe not in the first 2 or 3 chapters, but as the semester went on, because things became more obscure. Had I grown up, say, in the 1800s, I might have had a better understanding about all these different chemicals and what we could use them for and all that stuff. And then maybe chemistry would have had a little bit more reasonableness to make sense. But I never had that knowledge until I started reading Conversations on Chemistry, which literally was just a few years ago. So keep that in mind. So, for instance, we're going to talk about speed. And when I talk about speed, I don't want you thinking in terms of, okay, well, what's the definition of speed? What's the symbol we're going to use for speed? What's the symbols we're going to use to calculate speed? So, for instance, is speed about distance or is it about length? Well, are we going to use distance or are we going to use length? Well, they turned out to be a measurement of the same type of quantity. And then are we going to use time? And if so, is that going to be time in seconds or time? Those are all weird obscurities and stuff like that. What I want you to think of is, oh, we're doing speed. I know something about speed. I drive a car to work and it has a speedometer. I bet you that reads speed, and it does, right? And the first thing I'm going to ask you is, can one of you tell me, and y'all can type the answer in the chat or you can just say it out loud, but can anybody tell me what the units on your speedometer are?
Miles per hour.
Miles per hour. I will tell you repeatedly, and this is something to keep in mind when you're doing physics problems and math problems, and what my developmental math students used to call story problems. I call them word problems. But when you see the word per, I want you to automatically think divide, or specifically divide by. So when I say miles per hour, I'm thinking of dividing miles by hours. Now, is mile a unit of distance or time or mass or what?
Distance.
Okay. And hours, I assume, would be a unit of
Time.
time. Very good. So you might jump to the conclusion that speed is distance divided by time. And guess what? That's the exact right formula. Okay. So speed is distance divided by time. And that's exactly right. Now we're going to introduce something else. Speed is a quantity that starts with the letter S, and it is a quantity that we call a scalar, which also starts with the letter S. So keep that in mind. Again, we're always trying to get things in terms of things we already know. So speed starts with S, and it's a scalar quantity, which also starts with S. So I can remember speed as a scalar. Velocity, on the other hand, is a vector quantity, and it starts with the letter V, just like the word vector. So velocity starts with V, and vector starts with V, and both velocity and vectors are vector quantities. Okay. So now you can remember that the vector is the vector quantity, or the velocity is the vector quantity. Now, when I said speed is distance divided by time, technically what I meant is the average speed. At any point in time, if you're driving down the road and you look down at your speedometer, that's what your speed is at that instant. But if you drove for an extended period just on some trip, or even just, to the neighbor's house or something like that, If you then took the number of miles driven and divided by the number of hours it took to get you there, then you would get the average speed. Okay. Whereas looking at the speedometer would give you the instantaneous speed. Well, when you go to do something like that and calculate an average velocity, you're going to start to discover the difference between the vector quantity and the scalar quantity. In short, Vector from Despicable Me was right when he said that he named himself Vector because it's a mathematical term that means a quantity that has both magnitude and direction, right? So that's actually a good definition of a vector quantity. So when you're talking about speed, you can just read a speedometer and get your instantaneous speed, or you can use your odometer and a stopwatch and get your average speed, but that's all you need. Whereas if you're wanting to get your velocity, you could use the speedometer to get what your instantaneous speed is. But if you happen to have a compass mounted in your car, you could also find out in which direction you're traveling. So when you combine the speed that you're traveling with the direction that you're traveling, very precisely like 5 degrees east of north, then you could say, hey, I'm traveling at 30 miles per hour at 5 degrees east of north, and therefore you specified the velocity, okay? So your velociometer would be a combination of a speedometer combined with a compass, okay? Does that make sense? Now, the other weird part is we're going to define another quantity that's called your position vector. So, and when you do physics problems, a lot of times it will be helpful for you to create a coordinate system so you can make some sense of the world. So when I look out at my street, I look out it and I see my neighbor across the street and I see a golf cart going from my left to my right. I typically say up is the Y direction and to the right is the X direction. And what I mean by that is I imagine the X axis is going from my left to my right, where the right-hand side is the positive direction and the left direction is the negative direction. And then I imagine a vertical line, and upward corresponds to the positive Y direction and downward corresponds to the negative Y direction. Now, if I drew that or maybe put it on a big poster board or even a sign in my front yard, when my neighbor across the street looked at it, they would say, oh, but Billy's really weird. He's saying his positive X direction goes from right to left, not left to right. That's weird. But that's just because he's facing the opposite direction. And more importantly, that makes a very specific point that everybody's coordinate system is just fine. One of the ways you can state Einstein's principle of special relativity is that the laws of physics are the same for all coordinate systems. Okay, so that's something to keep in mind. Though you and I might not agree exactly what direction is positive X and what direction is positive Y, when we go to analyze the physics of it, we should get the right answer no matter what. So in order to do that, sometimes, like I said, we're going to have to create a coordinate system. That means us, in some sense, arbitrarily choosing where to put the origin, and then arbitrarily choosing a direction to point the positive x-axis in, arbitrarily choosing a direction to point the positive y-axis in, and then consistent with the right-hand rule, we're going to somewhat arbitrarily put a direction for the positive z-axis, but it has to agree with the right-hand rule, which means if you hold your fingers like this with your right hand, then if this index finger points in the positive X direction and then 90 degrees from it is this middle finger, that would point in the positive Y direction. Then your thumb, which is 90 degrees to both of those, has to point in the direction of the positive Z axis. So that's what I mean by a right-handed coordinate system. Just think of that. You always have to do that, and luckily you're not going to have to worry about that for a while before we get to 3 dimensions. But right now, just know that yes, you can put the origin at arbitrarily anywhere. You can point the x-axis arbitrarily in any direction. You can point the y-axis arbitrarily in any dimension, in any direction. But to be honest with you, you really need it to be perpendicular to the x-axis. Just to make life a little easier. And then you need the z-axis to be perpendicular to both. Okay. Now, once you have a coordinate system in mind and an origin in mind, then you can identify an object's position by drawing an arrow from that origin to the position of the person or the object or the thing. Now, if we're talking about things like marbles, then a marble's pretty small on the scale of humans. So we could just put an arrow from the origin of our coordinate system to the marble, and that's just fine. If the marble happens to be bigger than a marble, maybe it's like the size of a volleyball, then you might have to say, well, we'll point to the center of the volleyball. Or if it's a human, maybe we'll say, okay, we'll point to the center of mass of the human, which is somewhere behind the belly button, depending on, how your body's shaped and that sort of thing. But the main thing is there's a vector that we call the position vector, and it points from the origin to your position or the object's position you're studying. Then if the person or the thing chooses to move from that one spot, the initial position, and goes to a new position, then we have a new position vector that corresponds to the current position. That's another vector quantity. So we've got two position vectors. This is what I'm getting to. When you go to calculate the average velocity, unlike the speed where you just take the distance traveled divided by the time taken, when you do average speed, you've got to do something called calculating the displacement, which means we're going to subtract the final position vector minus the initial position vector. And we're going to get a new position vector or a new displacement vector. Okay. So in other words, we just imagine an arrow. Don't think about a vector as any more complicated than an arrow right now. When we get to chapter 3, we'll deal with what a vector is. But right now, just think of, and let me draw this on the notepad. Right now, I just want you to think of an arrow pointing from the origin to a point that an object is at time t = 0. And then think of another arrow from the origin pointing to where the object is after some period of time, delta t. Then the actual act of subtraction of final position arrow minus initial position arrow is just an arrow that is drawn from the initial position arrow to the final position arrow. So let me show you what that all means. I'm going to go ahead and share my screen. This will take about a second. Okay. So in terms of a coordinate system, you can imagine that's my x-axis, that's my y-axis. And then if I draw this at a diagonal, that's pretty much our way of specifying that the z-axis is coming out of the page. In other words, it's literally perpendicular to the page. So what I'm going to do is imagine an object is here initially. And then there is a position vector, which we'll call R, and that is the initial position vector. And as I said, you can just call it arrow or think of it as an arrow for right now. Now, sometime later, we could say this is a final position. And I mean after time delta t. Now we have a new position vector. Now, just to specify, I'm going to put a I on that to represent initial vector. And this is going to be R with an F on it for final. Okay. Now, what I'm telling you is there's another quantity called displacement. which is a vector quantity. And that displacement is supposed to be R final minus R initial. Notice I drew these symbols with subscripts. That's pretty normal. You're probably used to that. And if you've had any experience with vectors, you probably understand why I'm drawing the arrows over top of them. But that's what the arrows are, is to just indicate what that the thing is a vector quantity. Now the displacement is supposed to be R final minus R initial. And one of the things that you probably thought was worthless in pre-algebra and high school algebra 1 was the definition of subtraction, where they said A minus B is A plus the opposite of B. Did y'all think that was kind of stupid when they taught you that in pre-algebra and high school algebra 1? I was like, duh, of course it is. When you start talking about vectors, then that means something pretty substantial and helps you a lot, because what it means is you're going to take the RF vector and you're going to add to it the opposite of the R initial vector. And oops, there's supposed to be a negative in there. The negative wrote it in my head, but evidently did not actually write. So I'll put the negative there. And whenever you multiply a vector by a -1, you just make a vector that points in the opposite direction. So I'm going to say that this vector right here is -Ri. Okay. So if you see now, if you walk from the initial position along that -Ri vector, you go to the origin, and at the end of that arrow is the tail of another arrow. If you followed that arrow now, you'd end up at the final position. So the displacement vector is in fact the vector from the initial position to the final position, and this is displacement. So that's really what displacement is supposed to be. Okay. That being said, that's a little more complicated than we need, because we're using already at least 2 dimensions, if not 3 dimensions. And what I'm saying in chapter 1 is we're doing 1-dimensional motion. So we only have an x-axis, but it still applies. So for instance, you could have an x-axis just like this. You could say the origin is right here, and this is 1, 2, 3, 4. This is -1, -2, -3, -4. And then you could have a position vector as if this is the initial position. And then you could have another position vector as if this is the final position. And we just learned that we do the backwards of the initial one. So I'm going to say this is R sub I negative, whereas this is just R sub I. And this guy is R sub F. Again, this is the origin right here. So if we now add that to R sub F, you can see that the displacement vector is just a vector that draws from where you were to where you are. Points from where object was to where it is. Okay. So the difference between speed, which I already told you, average speed, is equal to speed with it. Notice I drew a bar there, not an arrow. A bar over top of a symbol generally means average. Another way we can do average is we could put it in a bracket like that. That also means average. So just keep an eye out for those. I generally use the bar, but occasionally I might have to use the brackets. But the average speed is distance traveled divided by time taken. Okay. And that's completely consistent with your speedometer. Okay. Now I'm going to tell you the average speed, or excuse me, average velocity. Is equal to, since it's a vector quantity, technically I should have an arrow over it, but since it's average, I got to put a bar over it. So I come up with that cumbersome writing, but that's basically it. And what it's supposed to be is the displacement divided by delta t. And remember, displacement is a vector quantity. Now, even if you know something about vectors, you probably know that you never divided by a vector, and you definitely never divided into a vector, at least with a vector. So this might abruptly scare you, but really all we mean is we're going to multiply the reciprocal of the time taken by the displacement vector. Okay. So what I would say is the displacement vector should have something a little better than having to write out the word. And in fact, what I'm going to say is the displacement vector will be called delta R. And the position vector will be called R. And of course, if you had an initial position, you call it a R sub I. If you had a final position, you call it a R sub F. Or you might call an initial vector R sub 0. That's another option as well. And some people even use the O because the O looks better than the 0. All of that's fair game. But now we have some pretty concrete stuff. We have an idea of average velocity. We have an idea of average speed. I will tell you that a lot of people try to say speed is the magnitude of velocity. And the vast majority of the time that's true. But if I gave you a true false question and I said, speed is the magnitude of velocity, you would have to answer false. Okay? Because if you think about the average speed and the average velocity, all it takes for you to figure out that they're innately different is imagine a t-ball player sitting at home plate getting ready to hit his ball off the tee, and he hits his ball off the tee, and you immediately start timing them, after which he immediately steps on home plate and then runs to first. And then, you know, the kids are picking flowers and other kids are running around throwing the balls in random directions. So he runs to second. And then other kids are fighting over who gets the ball. So he runs to third. And then some kid throws it in the completely wrong direction. So he runs back home and he steps right on the exact place on the home plate where he left. And you stop the timer. Now, in that case, if the kid was playing, let's say, t-ball, probably they were using like 60-foot bases. So he ran a distance of 60 plus 60 plus 60 plus 60. That'd be 240 feet. You divide that 240 feet by the time taken that you measure with a stopwatch, and that would be your average speed. Does that make sense to everyone? That's how you get the average speed, 240 feet divided by the time taken?
Yes.
Now, if you did that with average velocity, you would take a vector that pointed to that place on home plate, and then you would subtract that vector from, again, another vector that pointed to that exact place in space. So you would get two vectors that were identical subtracting from each other. So what's the difference of two identical vectors when you subtract them?
0.
Yeah, it's a zero vector. So you'd end up getting an average velocity of 0. So that's the major difference between at least average speed and average velocity, is because the velocity is displacement divided by time. If you make a complete loop and then take the average of it, then the displacement is going to be 0 and the average speed will therefore be 0. Okay. So I'll just remind you that by saying now that gets fast, but that's basically an idea. Whereas average velocity would be 0 divided by 12.0 seconds, which is the 0 vector. Okay, so that's one of the major differences. Again, though you don't have the tools yet to know exactly how we would deal with such a thing, if we were riding in a car and you wanted to express your instantaneous speed, you would just look at the speedometer and tell me you're going 32.8 miles per hour. If you wanted to tell me your instantaneous velocity, you'd say we're going 32.8 miles per hour at 15 degrees south of west. Again, you don't know how to deal with that extra little information I gave you, but that's okay. We're going to do that in chapter 3. But that's the difference between a velocity and a speed, at least instantaneously. Any questions about that? All right, so let's look at a couple problems. So how far can a vehicle travel in 3.50 hours if their average speed is 50 kilometers per hour? So the solution for this one is it's going to require us to use the idea of average speed is equal to distance divided by time. So what we're going to see is they want to know what distance you can travel. What that tells me is I'm going to say S average is equal to D over T. And I'm going to solve for distance by multiplying both sides by T, and I'll get S average times T is my distance. So the answer to the question is 50.0 kilometers per hour times 3.50 hours. Now, if I had given you that time in minutes, we'd have to either convert the kilometers per hour to minutes, or we'd have to convert the hours to, or the minutes to hours. The main thing is we just need them to cancel out. Of course, 3 times 50 is 150, and then 0.5 times 50 is 25. So this is 175 kilometers. So that's a very typical calculation that you should be able to do. And of course, that's the case with every equation you learn. You should be able to solve that equation for any of the variables in it. So for instance, one of the ways we have is average speed is equal to distance divided by time. Another way we have it is distance is equal to average speed times time. And another way we could have it is time is equal to distance divided by average speed. All of those are equivalent to one another, but I've taken the time to algebraically solve one for the other. Okay. Now that is sort of the holy grail too. Notice how I solved in variables for the term I wanted to solve for before putting the numbers in. That's really ideally what you'd like to be able to do as a physicist or engineer, but don't feel like it's required. Just make that something you're aiming to be able to do, but until you feel comfortable doing it, just plug the numbers in and solve it any way you can. Okay? Now let's look at another example. It says a biker travels at a constant 15.0 kilometers per hour for 30.0 kilometers. He then speeds up to 25.0 kilometers per hour and rides another 45 minutes. What's the biker's average speed? So this is not unlike one of the problems in your book, but I changed it up quite a bit as I did with the last one. I'm making it a little more complicated. What I need you to see here is that the average speed is defined to be distance traveled divided by time taken. No matter what information we gave you, like if I gave you 15 different speeds, you're never going to add those 15 speeds together and divide by 15. That is the average of the speeds, but that is not average speed. Okay. So always, always, always speed average S bar is equal to distance divided by time. So for the first part, what we can figure out is how far did the thing travel. It says a biker travels at a constant 15 kilometers per hour for 30 kilometers. So we actually know the distance there, but we don't know the time. In order for us to calculate the average speed, we need the total distance and the total time. So I'm going to need the time there. So if I solve for time, I get time is equal to distance divided by average speed. So I'm going to take that 30.0 kilometers and I'm going to divide it by 15.0 kilometers per hour. And from that, you can see the kilometers cancel out. And I'm ultimately left with 30 divided by 15 is 2.00 hours. And the distance traveled is equal to 30.0 kilometers, because we're going to need that for the first part and the second part so we can figure out the total distance and the total time. Now for the second part, and I mean second part of the travel, in that case, they gave us the speed and they gave us the time. So we're going to need the distance. In that case, we're going to say distance is equal to average speed times time. So that's going to be the 25.0 kilometers per hour times. Now here, if I multiplied by minutes, that wouldn't cancel out the hours below. So I've got to actually convert the hours, the minutes to hours. You probably know it's 0.75. I will show you in detail exactly what we do just to keep you all on the same page. We're going to say that's 45.0 minutes. I'm going to put the minute over 1, and then I'm going to say that 1 minute, or excuse me, I'm going to say that 60 minutes is equal to 1 hour. And now you can see that this minute cancels out with that minute, and then this hour cancels out with that hour. So we do ultimately get a certain number of kilometers out. So 25 times 45 divided by 60, which of course 45 divided by 60 rounds to 0.75. So that shouldn't be a problem. I'm going to say 25 times 0.75. Again, we get 3 sig figs. That means the distance traveled is 18.75 kilometers, but that 5 is an extra sig fig. So what we got is the distance is equal to 18.75 kilometers, and the time is equal to 0.750 hours. Okay. Now we can calculate the average speed. That's just distance divided by time. So the distance traveled is the 30.0 kilometers plus the 18.75 kilometers divided by the 2.00 hours plus the 0.75 hours. That's a zero down there. So this is going to be 48.75 kilometers divided by 2.750 hours. So 48.75 divided by 2.75 gives me 17.72 kilometers per hour. Now that was 3 sig figs divided by 3 sig figs, so we should only get 3 sig figs. So I'm going to say that the average speed was 17.7 kilometers per hour. And that's the right answer. Anybody have any questions on that? Okay, so that's a very typical type of problem that you should be able to solve. In your book, they do just like it, but in that case, let me see what they did. They said a car travels at a constant 50 kilometers per hour for 100 kilometers. It then speeds up to 100 kilometers per hour and is driven another 100 kilometers. What's the average speed for the 200-kilometer trip? So that one, you just have to take 200 kilometers because they gave you the total distance and divide it by the total time taken. A car driving at 50 kilometers per hour takes 2 hours to go 100 kilometers, whereas a car going 100 kilometers per hour takes 1 hour to go 100 kilometers. So the total time is going to be 3 hours, and we're going to take 200 divided by 3. So we're going to get 66.6 kilometers per hour. Okay, so that's the problem your book did, which is still not trivial. It's not the easiest the easiest average speed calculation, but it is a little bit easier than the one I showed you. Anybody have any questions on that? All right. Here's another one. During a time interval of 4.00 seconds, a runner's position changes from x1 equals 50.0 meters to x2 equals 33.5 meters. What is the runner's displacement? Okay, so we're now asking about that displacement. Displacement is remember, we called that delta R, and that's supposed to be R. That's supposed to be R final minus R initial. And specifically, they're supposed to be vector quantities. But in terms of the X and Y are all along the X axis, that just means in principle, one could be a negative and the other could be a positive. And the negative one means it's pointing to the left, and the positive one means it's pointing to the right. In this case, they're both positive. So what I'm going to say is delta R is equal to R final minus R initial, but R final is equal to X2. Notice I left off the vector symbol, and that's 33.5 meters. And R initial, why did I write a 5 there? What the heck? That was supposed to be an F. I have no idea how I made that into a 5, but oh well. X1 will be R initial, and that's 50.0 meters. So delta R is going to be 33.5 meters minus 50.0 meters. And that is equal to negative 16.5 meters. So the displacement delta R is equal to negative 16.5 meters. And notice the negative just tells us, oh, the person went from 50 meters, which would be 50 meters to the right, to 33.5 meters, which would only be 33.5 meters to the right. So the person clearly went to the left, which is not unlike the motion detector lab that you guys are going to do this afternoon, or did y'all do it the other day? Or need no,
Tomorrow.
tomorrow. Okay, gotcha. So you will see that tomorrow. You will have an idea where there's a motion sensor, and when it's something's going away from the motion detector, that's the positive direction, and when something's going towards the motion detector, that's the negative direction. Okay. So now we have another one. During a time interval of 4.00 seconds, a runner's position changes from 50.0 meters to x2 equals 33.5 meters. Sounds familiar, right? What is the runner's average velocity? So this time I'm going to say solution V average is equal to delta R over delta T, because we've learned that delta R is the displacement. Which is going to be equal to x2 minus x1, basically. And we already know what that is. So I can say V bar average is going to be negative 16.5 meters divided by 4.00 seconds. And of course, 16 divided by 4 is 4, but 16 or 0.5 divided by 4 is 1/8. Yeah. 2 times 4, yeah, 0.125. So I'm going to say this is negative 4.125 meters per second. But we only had 3 sig figs, so that 5 is a non-significant figure. And notice this negative sign indicates runner is running in negative direction. So whatever direction you chose to call positive, he's going the opposite way. Any questions on that one? Okay, so this is all the sort of stuff that we're doing with regards to velocity and speed and that sort of thing. Okay. The other level that we go to is acceleration, but I should pull back for a second and just mention Galileo was probably, as best we can tell, the first person to come up with an idea of what speed is. We never really made a distinction between speed and velocity because the idea of vectors wasn't really created until like the mid 1850s, the mid 1800s. So somewhere between 1830 and 1860 was when vector calculus was actually created, and vectors in general were created. So we didn't really have that back in Galileo's time, but Galileo, having been shown the instruments with which they would cut his entrails from his gonads, he was threatened with that, and he decided to maybe act like maybe the Earth did not move, and maybe the Earth is at the center of the universe. And at that time, the universe basically meant about 10,000 stars, and 7 heavenly bodies if you excluded the Earth, that sort of thing. So he basically recanted, and luckily, the person that had given him the permission to write the book that got him into trouble in the first place was a cardinal at that time. And in the meantime, he had become the Pope. So the Pope sort of said, I think he might have put his foot on the Inquisition trial people and suggested that he could do just fine with in-house arrest, because he was sentenced to in-house arrest for the rest of his life. And he was already like in his, I think his 70s at that time. So he took in-house arrest, and they advised him that he wasn't able to teach anything about the motions of the heavens anymore. What had happened was he had read about I think it was a Danes by the name of Hans Lippershey or Lippershey or something like that, who had actually created the first spyglass. And he read about this and made one himself and made it better. He did not invent the telescope. Galileo did not invent the telescope. I know a lot of people learned that in grade school, but that's not the case. But he did make it a little better. And he also is among the first people to ever turn that quote unquote spyglass that we now know of as a telescope. He was among the first people to turn that towards the heavens. There was another physician slash scientist that came to what we now call Manteo, North Carolina. And that particular person, it seems, may have very well created a spyglass and turned it towards the moon even before Galileo did. But, being in the backwaters of America, much less North Carolina at the time, was not a good way to publish your stuff. So we didn't know about it for a long period of time. I've forgotten his name now. I wish I could come up with it. I should know it, but I don't. But anyways, that person might have actually beat Galileo to the punch, because he did, in fact, catalog his visions of the moon and stuff like that. But Galileo did, like I said, took that spyglass, and one, he tried to sell it to the government for the military, and he did, and he made money, and that was really an important thing for him. So he used a lot of his inventions, discoveries, and stuff like that to make money. But he did actually turn it to the skies. And one of the things he noticed was that the planet Venus actually had all of its phases. And that was really problematic, because the Ptolemaic model of the universe had that the Earth was at the center, and then there was a crystalline sphere centered on the Earth around which the moon orbited. And then there was another giant crystalline sphere centered on the Earth that originally, in the early models of the universe, would have had Mercury on it. But we had discovered that when you look up in the night sky and you see, let's say, something like this in the night sky, I'm drawing a specific constellation now, okay? You see that, and then one year you go out at night and you see that all of a sudden this particular constellation that we know of as Gemini all of a sudden has an extra guest star in it. You say, well, that's weird. And you watch it for several weeks. And what you figure out is that over the next couple of weeks, that guy wanders around in a little loop. And it seems to wander through the constellations. The Greek word for wanderer is planetos. So they name these things the planets. And in order to account for Mercury doing that, they couldn't have Mercury orbiting the Earth in a crystalline sphere like that, because it would always go left to right or right to left. It would never make a loop. So they decided to take and make that first loop I've already drawn, they called that the deferent. And I have no idea if I'm spelling that right. It doesn't matter too much. But they created on that the center of another loop, and that loop was called the epicycle. And that loop was like this. And Mercury would travel around the epicycle in that direction. But here's the weird thing. It turned out that Mercury never got more than, I don't know, I think it's like 32 degrees from the sun. So they had to account for that. And Venus never got, actually, it might have been 36 or something, but Venus never got like 40, more than 42. So they had to account for Mercury and Venus behaving the way they did. So they made another epicycle and deferent for Venus. And this one's the epicycle. And then they made another epicycle for Venus. And then the sun was out here. And what they did is they imagined a line coming from the center of the sun to the center of the earth, and the center of the epicycle for Mercury and the center of the epicycle for Venus always had to be on that line. And that was the way they accounted for that loop. It turned out that Mars, Jupiter, and Saturn made those loops too, but they were able to stretch quite a ways farther from the sun. So they just had epicycles and deferents, but they didn't have that weird line. And then over time, they kept tweaking this thing to make sure it matched all the data from the past. And therefore, they would use it to project the data in the future so that kings and queens and monarchs and royalty and wealthy people could make good decisions based on what they thought was an accurate measure, specifically astrology, which we now know of as a pseudoscience. And, you know, things like what constellation your birth or which of your birth constellations is the planet Mars in matters as to whether you're going to get to marry someone or whether you're going to make peace with another country or go to war or something like that. So they made their money by predicting where the planets would be, you know, like 10 years in advance. And this was really complicated. And in fact, they ultimately not only had all this stuff, they even had an equipoint next to the sun and I mean, next to the earth at the center. And from there, you could look out into space and see that the planets were moving in a uniform motion. Whereas if you did it from the center, it wouldn't be uniform motion like Aristotle had done. So it's just a nightmare. Kepler was reported to have said, if I had been around when God created the universe, I would have asked him to make it a little less complicated. At the time that Copernicus comes along, there's literally like 89 spheres and feet inside of spheres. And that's also a reference, by the way, to A Bug's Life. So if you ever saw A Bug's Life and they talk about tunnels within tunnels, they were referencing the Copernican revolution. But Copernicus says, hey, no, we've lost our way from what Aristotle taught us. We've got epicycles and deferents and spheres inside of spheres and equipoints and imaginary lines. I think we've lost our way. He said, I can make the universe a lot simpler by just putting the sun at the center. And then the reason for Mercury repeating its motion in the sky in such a small period of time is the fact that Mercury orbits the sun closest to the sun. And then Venus is second closest, then Earth. And of course, the moon orbits the Earth. And then outside of that is Mars. And then outside of that is Jupiter. And then outside of that is Saturn. And including the sun and the moon and those planets, that's how we have the 7-day week. Each of those names, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday, can be traced back etymologically to the names of the planets. So that's why we have a 7-day work week, or excuse me, a 7-day week. Now, when Copernicus did that, he didn't do that because the science. He did that because he was appealing to authority. So I call the Copernican revolution an entirely separate revolution than the scientific revolution, because Copernicus didn't do it for science. He did it because he thought we had lost our way away from Aristotle. So he wasn't willing to imagine the planets speeding up or slowing down in their orbits. He wasn't willing to make the orbits anything other than circles, which are parts of a sphere. And because of that, he never got it precisely accurate. Kepler comes along later and does it. One of the major things that Copernicus also noticed, in addition to the phases of Venus, which you can see right here, the phases of Venus, if I put, let's say, Venus right here, then the half of Venus that's bright is the white half. And then, of course, if we put Venus down here, the half of Venus that's bright is the top half. And then if we put it over here, the half of Venus that's bright is that half that I don't have any color in. And then, of course, the half of Venus that's bright here is the top half again. So we're only going to see a crescent Venus over on this side, or a crescent Venus over on this side, or a new Venus, and all the other spots are the two spots above and below. But when Galileo saw all the phases of Venus, he knew this model wasn't right. Now, one of the reasons that they used this model was that Anaxagoras had actually postulated the idea that maybe the sun's at the center. And this is like, I think on the order of 100 BCE, or it may have been 50 CE, after what we normally call AD. So it was somewhere in that time period. But basically he said, if the Earth is actually moving around the sun, then just like your finger, if I look with my right eye, I see my finger being right here in the middle of the screen. But if I look with my left eye, I see it being over here beside the monitor. So when the Earth is over here, it should see a star be in one field, but when it's over here, it should see a star being in the other field. So if Earth is really orbiting around the sun, we should be able to look at some stars in the distance and see them wobbling back and forth. That's called parallax. And he didn't see that. In fact, they tried to see it and they couldn't see it. And he said, one of two things must be true. Either the universe is really, really ginormous, so big that we cannot detect the motion of the distant stars. That turns out to be the right answer, by the way. Or two, the Earth is not moving, and that's what he ended up choosing. They just could not imagine the universe being that big that we couldn't even detect the motion of the stars. So that's why we went with it. And then there was other data too. For instance, people thought in terms of Aristotelian physics that if a bird's sitting on a tree limb and sees a worm, and he jumps off the tree limb to go fly down and get the worm, then if the Earth is actually orbiting the sun, it'll leave the bird behind and he'd be left out in space. That doesn't happen, so they assume that the Earth must not be moving. But that was really the whole problem. They didn't understand motion. But Galileo took his telescope and looked at Jupiter, and in all the models of the universe, not one of them had Jupiter sitting still, but he found that Jupiter had 4 moons, what he called the Medicean moons. We now call them the Galilean moons, Io, Europa, Ganymede, and Callisto. And he saw that they constantly stayed with Jupiter. So for exactly the same reasons that those satellites stay with Jupiter, the bird would not be left behind by the Earth. That's why he chose the remainder of his life to study motion, so he could make sense of what he had discovered about the Keplerian model of the universe. So Kepler comes along, we'll learn about this in chapter 5, and basically takes Copernicus's model and says, okay, I'm not going to stick to Copernicus' stupid idea of not speeding up and slowing down and only having circular orbits. I'm going to do whatever the data tells me. And he ended up getting it right. Okay. So in that process, Galileo invented the idea of speed. And he basically defined speed as the distance traveled per unit time. And he also defined constant speed to be any kind of motion that went the same distance in a given interval of time. Like if you chose the interval of time to be 1/10 of a second, and you measured over 1/10 of a second that the object went 5 meters, then every 1/10 of a second, it should go another 5 meters and another 5 meters. That's constant velocity or constant speed. He wouldn't have differentiated. He also defined constant acceleration. Constant acceleration is anytime an object changes its speed by the exact same amount for a given interval of time. So for instance, if you dropped an object without air resistance, it would go from 0 to about 32 feet per second at the end of 1 second. If you waited another second, it would increase by another 32 feet per second. So now it'd be going 64 feet per second. If you waited for another second, it would be going 96 feet per second. That's the definition of constant acceleration. All of that was given to us by Galileo, and from it, he was able to come up with our first law of what he called Galileo's law of inertia, what we ultimately call Newton's first law of motion. But all of that pointed to basically understanding motion. So what I'm going to do with the remaining 5 minutes is I'm going to use some information we found out. When you do have your lab, you'll discover this. But if you make a position versus time graph, and let's say we measure position with the quantity x, if I did something like this and made a graph like that, then the height of this point right here is really the distance from the origin. And if it happened to be a curve like this, then that distance is still the same thing, but it's negative, meaning it's on the other side. Another thing is if you took that point right there and you drew a tangent line, then the slope of that tangent line, which by the way has units of rise, which are meters, over run, which are seconds. So the slope is the velocity. And I mean velocity, not Galileo's term, literally velocity, because it gives you a positive sign if the thing is going in the positive direction, or it gives you a negative sign if the thing's going in the negative direction. So from that, we can see that v is equal to dx dt, which is really the limit as delta t approaches 0 of delta x over delta t. If we go further and make a plot of velocity versus time, we again could get, now in your lab, they're only going to have straight line motion for velocity because we only study up to constant acceleration. So they won't have any curves, but they could have straight lines like that. And again, the height in this case is the velocity. And down here, it would be the velocity as well, but that's a negative velocity. But we also have the slope. And if you look at the slope, the rise is in units of meters per second, and the run is in units of seconds. So we actually get the units of acceleration, which is meters per second every second. And that allows us to reach the conclusion that A is equal to the limit as delta t approaches 0 of delta v over delta t, which is dv over dt. So going this way, we have to differentiate. Going this way, we have to integrate.
Preheat the oven.
Your microphone's on there, Jennifer. All right. So let me show you really quickly. We don't have much time, but if we start with A, if we start with A equals a constant, hey, I don't know what's going on here? That's weird. Everything started disappearing. So I guess I'm going to call that a day. I'm going to go through starting with integrating A equals a constant, and I'm going to derive a kinematic equation. And then I'm going to set that new result to equal to V, which is dx dt. I'm going to integrate that and come up with a new kinematic equation, but I'll do that next time and I'll work some more examples for you. So make sure everybody has chatted me your first and last name. You guys are free to go. Please check and notice that I did change your due date on chapter 1. Chapter 2 homework, I think, is in a pretty good spot because by Monday of next week, we'll be completely finished with chapter 2. So you guys are free to go. Thank you for coming, and feel free to send me any messages if you have any questions or anything like that.
Thank you.
You're welcome. See you, Jennifer.
Bye.
I'll wait for the last person to leave just in case anybody has any questions. I did see that people were actually answering my questions in the chat. I'm sorry the window wasn't open and I didn't see it till now. Joshua or Diego, do you guys have any questions? I'm thinking y'all might not be here, but just in case, I figured I better ask. It looks like that's it. All right. Well, have a good one, everybody. Bye-bye.